So several of the next sample problems in Chapter 6 deal with this concept of heat capacity, or heat that's given off or taken in by a physical or a chemical process. And we can figure out that heat and relate it to delta H experimentally by measuring the heat lost or gained by a reaction, and again that can be a physical change or an actual chemical reaction, using this equation. Q equals C times M times delta T. So again, Q being heat, C meaning heat capacity, M as in mass, and notice this is not an italicized M. A regular M is going to refer to mass in grams, and then delta T. So that's going to be an equation that we'll see for several sample problems, and we'll see different ways that we can use and kind of manipulate this, talking about physical changes, chemical changes, calorimetry, and so forth. Okay, so for this problem, and again, you always know I like to draw pictures sometimes to help us think about things that are going on. If you've ever looked at really good cookware, you'll see that it's what's called copper clad, or they'll have some copper that's on the bottom. So you'll kind of have your skillet that's here, and kind of layered on the bottom is going to be some copper. And so that they tell us we have a skillet here that has copper on the bottom at 125 grams, and that's the mass of copper that's there. They also tell us that the specific heat capacity of copper is 0.387 joules per gram Kelvin. One of the things just to note, if you remember what the specific heat capacity of water is, it's 4.187. So this is almost 10 times less than that value. So what that means is to heat this stuff up, you need 10 times as much heat as you need to heat up water. So all it really means is that copper heats up very easily without a lot of energy input. And that means it's really good for heating up quickly and transferring heat very easily to whatever it is that you're cooking. Okay, so we've got this layer of copper that's welded to the bottom of a skillet, 125 grams of copper. We want to know how much heat is needed to raise the temperature of this copper layer from 25 degrees to 300 degrees C. So again, the question is how much heat? When we're asking about heat, we want to know what Q is. And so again, this equation that's going to relate to a lot of the problems we'll deal with in the next few sample problems is Q, that is the heat, is equal to the specific heat capacity times the mass times the change in temperature. Well, they gave us the mass of the copper that we have. They gave us the specific heat capacity. Anytime you see a delta, remember that the delta equals final minus initial. So this is the final temperature minus the initial temperature. Delta T in this case is going to be 300 degrees C minus 25 degrees C. Okay, and so delta T is going to be equal to 275 degrees C, and that equals 275 Kelvin. And you're going to say, whoa, Dr. Prenny, don't you need to add 273 to that? Remember, if you're taking the difference between two centigrade temperatures, that's going to be equal to the same magnitude, the same value as if you were to take the difference in Kelvin. Convince yourself for this, right? That if you converted this one to Kelvin and then this one to Kelvin and then subtracted them, you'd still get 275. I want to just take a second and kind of refresh your memory. This is back from Chapter 1. This shows the Celsius scale, the Kelvin scale, and the Fahrenheit scale. So we're not going to look at the Fahrenheit scale right now, but look at Celsius and Kelvin. We can see that to boil water from an ice cube, we'd have to increase it 100 degrees C. Do you see that the same temperature difference in Kelvin is 100 Kelvin? So the magnitude of the difference between those is the same. Now here's the thing. You actually can do this problem and not get in trouble if you converted each of these temperatures to Kelvin and then subtract them. What you want to make sure you do not do not add 273 Kelvin to this and say that that is going to be your delta T. You will get the wrong answer in that way. Again, if you wanted to, you could see this, that you could take delta T equals T final minus T initial. If you converted each of these to Kelvin, 573 K minus 298 K, you still get 275 K. So again, if you want, you can convert them, but you're taking an extra step that you don't need to. The magnitude of the increment difference in Celsius and Kelvin is the same. All right, so we know the heat capacity, we know the mass, we know the change in temperature. We can use that to calculate heat. And again, we're going to be very careful with our units on these problems because we need to make sure that everything is in the right units or we're going to be off again in our answer. So Q is going to be equal to 0.387 joules per gram Kelvin. We can already see that we've got things in the right units. We have our mass in grams, so that's 125 grams, and 275 Kelvin. Go ahead and just multiply those together to get to Q, and you get 1.33 times 10 to the 4th joules. So again, this is the amount of heat that's given, that is required. Notice this is a positive value. This is the amount of heat that's required to be put into the system. Q being positive means heat that needs to be added. And that makes sense, right? We need to add heat into our system in order to raise the temperature of that skillet from 25 degrees C to 300 degrees C.